Hello, Math 1090 class. Today I'd like to start talking about section 6.4, Amortized Loans. In this section, we will explore conventional loans, also called amortized loans, or installment loans. Examples include auto loans and home mortgages. One great thing about loans is they use the exact same formula as a payout annuity. To see why, imagine that you had $10,000 invested at a bank and started taking out payments while earning interest as part of the payout annuity. And after 5 years, your balance was zero. Now flip that around and imagine that you are acting as the bank and a car lender is acting as you. The car lender invests $10,000 in you. Since you're acting as the bank, you pay interest. The car lender takes the payments until the balance is zero. So again, I'd like you to see this as the same as a payout annuity, just the role of the lender and the payee have been switched. To start with amortized loans, let's get into some definitions. So first, an amortized loan is a conventional loan where you make equal payments on a regular schedule, usually monthly, to a bank and are paying interest on the loan. So here is your payout annuity formula where I have changed this letter here. I think in our payout annuity formula, this was a W, the amount of a withdrawal, but now I'm going to represent it as a payment. So again, P is your balance on the account at the beginning. Your payment is the amount of your loan payment. R is your annual interest rate in a decimal form. T is the length of the loan in years. And K is the number of compoundings in 1 year, and normally this will be 12 times per year. Let's look at our first example. You have decided to buy a new car and determined that you can afford $200 per month as a car payment. If you get an auto loan at a 3% interest rate for 60 months, which is 5 years, how expensive a car can you afford? In other words, what loan amount can you pay off with these $200 amount payments? So in this problem, we get to use the formula directly as it's given, because notice your payment is already on the right-hand side of the equation, and P, the balance, what you can afford at the beginning, is already on the left-hand side of the equation. So we'll just use this equation directly as it's given. So here we go. Your principal, your initial balance that you can start, well, it's going to be your payment, the $200, times the 1 minus 1 plus. It's going to be your interest rate as a decimal, so 0.03, divided by K, the number of times that we compound interest per year, which is going to be at 12, raised to the negative 12 times 5, because we're doing this in years, 5 years, divided by the interest rate, divided by 12. Okay, let's grab our calculator. Now again, your calculator may be slightly different than mine. If you're unsure about the use of parentheses, feel free to insert extra parentheses here, just so your calculator knows that this is all the numerator of your fraction. Notice the denominator already had a set of parentheses there. So I'll go ahead and put a starting parenthesis. 200 times 1 minus parenthesis 1 plus 0.03 divided by 12, closing parenthesis that starts the interest rate portion of this. Now I need to get the exponent. My calculator uses the caret key. Now, depending on your calculator, you may have to put another set of parentheses around this exponent. You may have to put parentheses here. I don't have to because my calculator clearly shows that this is an exponent. So I'm just going to write the negative 12 times 5. Now I'll get out of the exponent by pressing over. And I will put the bracket or a parenthesis and another parenthesis to close off the numerator, the top of the fraction, divided by 0.03 divided by 12. Okay. I get a principal or an initial balance of a car to be $11,130.47. This is the price of a car that you can buy and end up having your $200 month payments. Okay, let's look at another example. You want to buy a car that costs $18,000. The dealership is offering a 2% interest rate for 48 months, 4 years. What will your monthly payments be? Okay, so here we're not given the formula exactly as we need it. Now we are given this formula. It says if P, remember P is your initial balance. If this is equal to your payment times your 1 minus 1 plus your interest rate divided by the number of times you compound interest per year raised to the negative KT, all divided by R over K. Then we need to rewrite this formula or solve it for your payment amount. Now we did this back in modules 6.3 and 6.2. So remember the way we did this is we took the denominator there, R over K, multiplied it to hit the P term, and then we divided by this bracketed expression. Now I showed the algebra more slowly there, so here I'm going to just do a shortcut of it. I'll multiply to get the R over K next to your P. And then divide by that bracketed expression to write it as 1 minus 1 plus R over K to the negative KT. This is our formula. Solve for your payment amount. And now let's put our information in. The P, the initial balance, the $18,000. Times your interest rate, 2%, write it as a decimal. Divide by 1 minus 1 plus your interest rate divided by 12 raised to the negative 12, and we're doing this for 4 years. Let's grab our calculator. So again, just to help with your grouping symbols, depending on your calculator, you may need to have a grouping symbol for this numerator. I don't think you will, but you know, just be cautious. So, parenthesis, the $18,000 that your car is going to cost times the 0.02 divided by 12. The parenthesis to close off your interest rate, another parenthesis to close off the numerator, that red one that I wrote there, divide by bracket, parenthesis, 1 minus 1 plus 0.02 divided by 12. Now this parenthesis here will close off this one that's right here. Now I need the exponent, negative 12 times 4. Arrow over to get out of your new exponent, and then this parenthesis here will be corresponding to this bracket that's at the end. Okay, and I get $3.90, and if I round this to the nearest penny, 51 cents per month payments for this $18,000 car. Okay, let's try another example. You want to buy a $227,000 home, and you can pay 15% as a down payment, which means you're not actually borrowing the entire $227,000 because you're going to put some of this, your down payment, down ahead of time. So you'll finance less than this. Then you'll take out a 30-year loan for the remainder. Now, I'd like to give you a moment to work this exercise on your own. So if you could pause this video, give a shot to see how well you do, and then come back and then we'll work on it together. I'll see you in a moment. Okay, let's see how you did. So piece by piece, let's start with part A, of course. How much is the loan amount going to be? So you're not actually taking a loan out for the entire $227,000 because you're going to pay 15% as a down payment. So your loan amount. If I could spell amount, A-M-O-U-N-T. Well, if you're putting out a 15% down payment, then you're only going to finance the remaining 85%. So I'm going to go 0.85 times your $227,000. So 0.85 times 227. Your loan amount is going to be for $192,950. Okay. Now part B. What will your monthly payment be if the interest rate is 5%? So I'm just going to grab our loan formula that we had earlier, and I'm just going to write down already solved for the payment amount since we've done it twice now. So your payment amount is going to be your original balance P times the R over K, all divided by the 1 minus 1 plus R over K raised to the negative KT. Now your initial principal, that's the $192,000 loan that you're going to take out. Times your interest rate, which will be 5%, written as a decimal. Divided by the 1 minus, the 1 plus, raised to the negative. Don't forget that negative sign. This would be 12 times the term of the loan, which was 30 years. Okay, grab your calculator. So 192,000. Oh, I wrote the wrong number here. I just recognized that. I said the loan amount was 192,950, but I wrote 250. Let's fix that real fast. This should not be a 2. $950. Okay, so 192,950 times the 0.05 divided by 12, divide by the bracket that I'm writing, but again, my calculator uses a parenthesis here. 1 minus, 1 plus, the 0.05 divided by 12. Now this parenthesis closes off this one here at the end. Now I need to do the exponent. The negative 12 times 30. Press the arrow key to get out of the exponent, and then this parenthesis here will close off the bracket that was at the end. Okay. So I get this will be $1,035, and if I round this to the nearest penny, and 80 cents, and this would be per month. Okay, last part of this. How much will you end up paying for the loan or for the home after the 30 years has passed? So how much are you going to end up paying? So I don't have a formula for this, but we can think our way through it. Your total paid. Well, we paid $1,035.80, and we did that for 12 months out of the year. And if we do it for the entire 30 years, then we'll end up paying a total of $372,888 towards the loan. So remember, we took out a $192,950 loan, but we ended up paying back $372,888. Now, this asks for how much we end up paying for the home. Now, depending on how you interpret this question, then maybe we should also think about including the original down payment of the home. So if we include original down payment of the loan, then we should add that portion of it. So what was the original amount? Well, we put a 15% down payment, so that would be 0.15 times your 227,000. So our initial down payment that we made was $34,050. And so if we add this to the amount that we paid on the loan, then I think we would have the $372,888 plus the $34,050. Then we would have paid a total of $406,938 for the house. Okay, now this seems a little expensive, but this is the cost of buying a house. Remember, we're buying a $227,000 house, but we don't have $227,000. So how do we afford our house? Well, we take out a loan, and we're going to be paying interest on that loan. We're going to be paying interest to use somebody else's money to buy our home. So we end up paying a total of $406,938 for this house. Okay. Let's look at another example. Consider the loan from the previous example. How long will it take to pay off your loan if you pay $1,200 each month rather than the $1,035 that we ended up paying? So what if we end up paying $1,200? We pay a little extra. How much money will be saved by making these $1,200 payments? Okay, I'd like to give you a moment to work this example on your own. So if you could, please pause the video, determine how long it's going to take to pay off your loan if you paid off $1,200 per month, and then figure out how much money you're going to save. And also, I'll see you back here in just a moment after you take a moment to work this on your own. Okay, let's see how we did. Now, I started already by writing our loan formula that we have. And let's see what we can do with this loan formula. This loan formula says, you tell me the payment and interest rate and the number of times we compound interest, and this will tell me the initial balance of the loan that you can afford. And so let's put in these values that we have. What if we make $1,200 payments? At our interest rate was 5% from our previous problem, raised to the negative 12t, all divided by the 0.05 divided by 12. And we want to know what time t will be when your P, your balance, is going to be reduced to, or it'll be 192,950. Okay, so what that's asking us to do is to solve this equation. We want to solve this equation for t. So what will be the new term of our loan if we make these larger monthly payments? Now, previously we had this set equal to 30, but we don't know what it is. We want to figure out how long it will take to pay off this new loan at this higher payment. Okay, so here we go. I want to solve this for t. I'm going to do two things in my first step here, just to reduce how much writing I'm going to do. I'm going to multiply this 0.05 divided by 12 onto this side to get rid of this fraction. And then I'm also going to divide by this $1,200 here. So I'll multiply to get this on the other side and then divide by this $1,200 coefficient to get it in the denominator. So if I do that, then we're going to be left with the 1 minus, the 1 plus 0.05 divided by 12 raised to the negative 12t. And this will be the 192,950 times this 0.05 divided by 12 divided by that 1,200. And to simplify our calculations a little bit so we don't have to keep so many numbers running around, let's figure out what this is on the right-hand side. 192,950 times the 0.05 divided by 12. And then I'll divide that by 1,200. Now, I'm going to have to write a decimal approximation to this, but I want to avoid rounding too soon. The more I round, the more error I'm going to introduce. So probably the best way is not to round at all and just use this original figure that I have. But I want to simplify how much I'm writing in our example. So I'm going to round this to 5 decimal places. And I think that'll be far enough to reduce a lot of my rounding error. So this would be 0.6699. And if I round to 5 decimal places, then this is going to be a 7. Okay. Okay, I want to continue solving this for t. So now solve this for t. I'm going to subtract 1 from both sides. That'll give me a negative 1 plus 0.05 divided by 12 raised to the negative 12t equals, and when I subtract 1 from this 0.66997, then I get negative 0.33003. Now I'm going to divide this side by negative 1, divide this side by negative 1 to get rid of this negative sign that we have here. So we get 1 plus the 0.05 divided by 12 raised to the negative 12t. Okay. And now I'm going to reference the work we did back in chapter 5. If I want to solve this equation for t, I need to get t out of the exponent. So we choose to apply a natural log to both sides. This will allow us to use the property of natural logs that let exponents become the coefficients of the natural log. So then we'll get negative 12t natural log of 1 plus the 0.05 divided by 12 equals the natural log of the 0.33003. Okay, we're almost done with this because now I want to get t by itself. Let's divide both sides of our equation by the thing that's not t, which would be the negative 12 natural log of the 1 plus 0.05 divided by 12. Also divide this right-hand side. I think what this will give us is t is equal to this value. And let's grab our calculator to help us with this. Again, I'm going to keep reminding you that grouping symbols are important. You're probably going to have to put a grouping symbol around this entire denominator so that your calculator knows that belongs in the denominator. So it'll be natural log 0.33003 divided by this parenthesis to start the red one I wrote for my denominator. Negative 12 natural log 1 plus the 0.05 divided by 12. Now I'll need a first parenthesis to close off this blue one that we wrote, and a second parenthesis to close off this red one that we wrote to group the denominator. Okay, and what I get is 22.2 years to pay off your loan. Now this is quite a bit of a time savings. Remember, before it was 30 years. We've just reduced our loan for our house down to 22.2 years. So what can I say about this if I put it all down? So paying $1,200 per month instead of the $1,035.80 pays off the house. Now, if I double check my math with this, this is going to be 30 minus 22.2. Oh, that's not right. 30 minus 22.2. It pays off the house 7.8 years faster. $7.8 years sooner if you pay off the make the extra payment per month. Okay, doing a little bit more comparison here, just so we can get an idea of what this means to us. The total paid on the house. Well, we're making $1,200 a month payments. We do that for 12 months, and we do it for 22.2 years. Oh, we should probably add to this the down payment that we made so that we can compare it to our answer from our last example. So plus the $34,050 from our down payment. So here we go. $1,200 times your 12 months a year times your 22.2 years plus your $34,000 down payment means now we end up paying $353,730 for the home. Now, if you compare that, remember, in our previous example, we ended up paying $406,000 for the home. So how much did we save? Well, let's start with how much that was on our previous problem, the $406,938. With the extra payments, we only paid $353,730. For a savings of $53,208, which is quite a lot of savings. So the question to ask yourself is this a reasonable thing to do? You are required to pay $1,035.80, but if you could end up paying $1,200, so maybe a little bit more, make a little bit extra of a payment each month, then you end up saving $53,208 over the life of your loan. And maybe as a single person, this might be a hard jump to make, but as a married couple, maybe that extra $165 is something that you'd reasonably be able to do. So definitely consider when buying a house, can you afford the extra payment each month to end up saving you a dramatic amount in the future, which maybe could go towards something else, like a retirement fund, something to benefit you when you decide to stop working. Okay, let's move on. I have one more idea to present to you. Remaining loan balance. With loans, it is often desirable to determine what the remaining loan balance will be after some number of years. For example, if you purchase a home and plan to sell it in 5 years, you might want to know how much of the loan balance will have been paid off and how much will you still have to pay when you make the sale of your house to pay it off. To determine the remaining loan balance after some number of years, we first need to know the loan payment amount, which is what we did in our previous examples. Then, to determine the remaining loan balance, we can think of, and this is the important piece, we can think of how much loan will these loan payments be able to pay off in the remaining time of the loan. In other words, we're looking for what P will be when T will be the remaining time. And this is the part that we're going to look at more in these next examples, is what is that remaining time left? Let's look at an example. A couple purchases a home that costs $180,000 at a 4% interest rate for 30 years with monthly payments. What will be the remaining balance on their mortgage after 5 years has passed? Okay, so first thing we need to do is, again, calculate their monthly payments. So I'm going to grab our formula that we have and solve for the payment amount. If we solve for the payment amount, then we have your payment is going to be, well, it's going to be P, your initial balance. Remember, I'm going to multiply to get this R over K onto the left-hand side. And then I'm going to divide by this bracketed expression. So it'd be 1 minus 1 plus the R over K raised to the negative KT. Okay, we'll put in our initial balance, the $180,000. Times our interest rate, which they tell us is 4%. Again, write that as a decimal. Raised to the negative 12. And we're doing this for a 30-year loan. Okay, grab your calculator, make sure you can duplicate these values that I have. So 180,000 times the 0.04 divided by 12. Divide by parenthesis the 1 minus the 1 plus the 0.04 divided by 12. Close that parenthesis that represents this parenthesis at the end. Raise to your exponent negative 12 times 30. Then you're going to get out of the exponent by pressing the arrow key and put another parenthesis that represents this bracket at the end. Okay, and I get a payment amount of $859, and if I round this to the nearest penny, 35 cents per month. This is what this home will cost you every month in a mortgage payment. Okay, now that we have the payment amount, now we can come back and figure out what is going to be the remaining balance after 5 years. So now we know the payments, we can determine the remaining balance. We want the remaining balance after 5 years. Well, after 5 years, that means there will be 25 years remaining on the loan. So we calculate the loan balance that will be paid off with the monthly payments over those 25 years. So now I use the formula directly as it's given. I'm going to write it down here for completeness. So here, P is going to be your payment amount. The 1 minus, the 1 plus, the R over K raised to the negative KT divided by R over K. And in this formula, again, I want to make sure that we identify that this time T is going to be the remaining time of the loan. So for us, it'll be the 25 years. So this will be the 859, 35, 1 minus, 1 plus, our interest rate, which was the 4%, divided by 12, raised to the negative 12 times 25, divided by the 0.04, divided by 12. So let's grab our calculator. So grouping symbol maybe to represent the numerator of your fraction. Your calculator may not need this grouping symbol, but I'm just trying to be explicit with us today. I'm grouping off this entire numerator. So 859.35 times the 1 minus, the 1 plus, 0.04 divided by 12, raised to the negative 12 times 25. Again, arrow over to get out of the exponent. One parenthesis here represents this blue bracket in my equation. A second parenthesis represents the red one that I wrote as a grouping symbol. Okay. And what I'm calculating now is that the remaining 25 years that we'll be paying for this loan if we kept paying for it, the remaining balance would be the $162,805. And if I round to the nearest penny, 99 cents remaining on your loan after 5 years of paying on it. Okay, let's look at another example. Consider you purchase a $34,000 car at 4.7% interest, compounded monthly for 6 years. What would be the remaining balance on your car after making the 28th payment? Okay, so here we go. First thing we need to do is figure out what will be the monthly payments on the car. Now, I'd like to give you a moment to do this on your own. So if you could, pause the video and determine what the monthly payments will be. Afterwards, come back, unpause the video, and we'll see if we agree. I'll see you in a moment. Okay, let's see how we did. I went ahead and worked the formula out on my own while you were busy doing yours. And again, notice that I started with my payment formula from our previous sections. And I evaluated this at the $34,000 at the 4.7% compounded monthly for 6 years, and I get a payment amount of $542.85. I hope you're able to confirm that. Now that we know the payment amount that we make per month, now we can look at answering the question that we started with was, what is the remaining balance after you make the 28th payment? Okay, so let's think about this 28th payment. And I have to kind of work this out to be able to reason what it's going to be. So here we go. The 28th payment. I want to convert this to a time in years, because when I put it into my formula, this T always represents time in years. So let's convert this 28th payment into a time in years. So a 28th payment would be 28 payments. I'm going to multiply this by a fraction that tells me in 1 year you normally make 12 payments. And if I keep track of units, I can identify that the units of payments and payments will cancel, and what I get back is going to be a time in years. So this would be 28 over 12. So 28 divided by 12. This would be roughly 2.33 years. But to avoid rounding, I'm going to go ahead and write this as an exact fraction. So my calculator allows me to rewrite this as a fraction of 7/3 of a year. Of course, you could have done this by hand. You could just say, to simplify your fraction, let's divide the top and the bottom by 3. 3? No, not by 3. I think we have to divide, because 3 doesn't go into 28. I think we need to divide the top and the bottom of our fraction by something that goes into both of these evenly. So I'm going to divide by 4 on the top and the bottom. So 28 divided by 4 is 7. 12 divided by 4 is 3. So this represents 2.3 or 7/3 of a year. This is what the 28th payment corresponds to. So then the remaining time on the loan, well, we were going to be paying this for 6 years. So now we have 6 years minus the 7/3 of a year. So 6 minus the 7/3 would be 3.666 years. But again, to avoid rounding, I'm going to convert this back to a fraction. And this corresponds to 11/3 of a year. That is remaining. Which is, 3.6 years, but I want it as a fraction, 11/3. So now let's determine what our payoff, our principal is going to remain on this loan. So let's grab our formula that we have. It's going to be P is going to be your payment amount times the 1 minus 1 plus the R over K raised to the negative KT divided by R over K. And again, when I write this formula, make sure that we're thinking that this T is going to be the time remaining on the loan. For us, it'll be the 11/3 years. So this is going to be the $542.85 that we're going to pay every month. 1 minus 1 plus. Again, our interest rate was the 0.047 divided by 12, raised to the negative 12 times the 11/3 of a year that's remaining. All divided by the 0.047 divided by the 12. So again, grab your calculator. Make sure we get this in there carefully. We have the 542.85 times the bracket, which is going to then have the 1 minus 1 plus the 0.047 divided by 12. This parenthesis represents the end of this parenthesis at the end of your interest rate, raised to the exponent. And I'm going to put parentheses here just to make sure we get this in here right. This will be negative 12 times the fraction 11/3. Notice I used another parenthesis for that fraction to make sure my grouping is done. And another parenthesis to close off the exponent. Then arrow over and write a parenthesis to close off your bracket. I think I put a parenthesis in the beginning for the top of my numerator. Let me just double check. I'm questioning if I need another parenthesis right there at the end. I did. I put a parenthesis to start my grouping symbol, or to start my numerator. So let's arrow back over. I need to put a parenthesis at the end of this. That one, that represents the close of my numerator, divided by, oh, I hit clear. That's terrible. If I can just bring that last result up again. I hit the wrong button. I got to type it all again. 542.85. 1 minus 1 plus 0.047 divided by 12. Parenthesis raised to the negative 12 times the 11/3 of a year that remains. Now, I had some issues getting this in my calculator. I hope you did better than me. So please confirm. But I think that the remaining balance on your loan is going to be $21,901.30. Remaining after you make your 28th payment. Okay, I have one more example for us to look at. This one says, a couple decides to invest in a rental property. They take out a loan of $240,000 at 3.7% APR, compounded monthly for 30 years. And they make payments of $1,104.68 every month. What would be the remaining balance after they make the 40th payment? We want to know the remaining balance after they make their 40th payment. So this problem is very similar to the last one, but I already told you what their monthly payment is to save us a little bit of time. But I'd like you to come up with what the remaining balance after the 40th payment on your own is. It's going to be very similar to this set of calculations that we did here. So I need you to duplicate this portion of our work for this couple that's investing in this rental property. I'd like to let you do this on your own, so if you could please pause the video and come back and double check what we get afterwards. I'll see you in a moment. Okay, let's see how we did. I went ahead and worked this out ahead of time while you were busy working out yours. Well, let's kind of go over what I did just to make sure that we agree. We wanted to find the remaining balance on the rental property after making the 40th payment. So first I decided to take the 40th payment and convert that to years. And I determined that the 40th payment correspond to 10/3 of a year. Now, if you didn't want to write this as a fraction, you could just divide 40 divided by 12. And the 40th payment corresponds to 3.33 years, so a little over 3 years. But to avoid rounding, I wanted to have an exact answer, so I divided both the top and the bottom of our fraction by 4. To get 10/3. Now, that's how much we paid so far. So what was remaining, well, if you had 30 years of a loan to start with, and you subtracted 10/3 of a year, then you would have the 30 minus the 10/3 of a year that you've already paid, which would have been 26.66 years, but I wanted that again as a fraction to reduce rounding errors. So I called that 83rd years remaining. Now we'll take our loan formula, and for the value of t, we'll have the time remaining, the 83rds of a year that remains. And so I plugged all the values into our formula, including our payment amount, our interest rate, compounded monthly for 83rds of a year. And I get that there'll be a remaining balance of $224,500.70 remaining after your 40th payment. Let's explore this a little further now. How much did the couple pay the bank during these 40 payments? So I don't have a formula for this, but we can just kind of think our way through it. I want to make this in blue so it all looks the same. Okay, so here we go. The total paid to the bank. Would they made payments of $1,104.68, and they did that for 40 payments. So 40 payments of this amount comes out to be $44,187.20 was made, or of payments was paid to the bank. Okay. How much of the 40 payments actually went towards the loan? Well, remember, they're making these payments, but this does not mean the loan was reduced from $240,000 by $44,000, because notice the loan only went from $240 to $224. So how much actually goes towards the loan? Here I'm going to look at your change in balance. We started with a loan balance of $240,000. Oh, I missed a zero. We started with a loan balance of $240,000. But at the end of the 40th payment, we only reduced the loan to $224,500.70. which means the loan, or the money that actually went towards the loan, was $15,000. $15,499.30 actually went to the loan. The rest of the $44,000 would have gone towards the interest. So they calculate how much interest they paid during these 40 loans. Then your interest paid, well, it'd be that $44,000 that they actually gave the bank, $44,187.20, minus the portion that went towards the loan, the $15,499.30. Which tells us the remainder of this, the $28,687.90 went towards interest payments to the bank. Okay. This finishes all of the notes I have for you for section 6.4 amortized loans. So I'm going to stop this video here. We have one more video to cover for our class, section 6.5. I will do that next time. And so I will see you then. Have a good day.